All right, this is my actually third time trying to record this because I keep getting technical difficulties, but hopefully this is the one that works. And also, all it means is that I'm a pro at explaining this now. Let's get to it. Tangent line equations. All right, let's get started. Let's do that correctly. Okay, first of all, the question is or the skill we're trying to be able to do here is start with a parametric equation. I'm just going to be writing like random things out. BT plus E, F, G. Wait, that's not how the alphabet works. Plus. Forgive me if I'm a little bit tired after doing this 3 times. Anyway, we have a parametric equation, and our goal is to be able to take this parametric equation and find the tangent line at any given point of this parametric equation. Now, just to quickly draw out what that actually means, say we've got, let me make that nicer, z, x, y, and some line that travels through it. If we want to find, or we want to be able to find a tangent line that touches really any point, like that, like that, like that, anywhere on this graph. Now, to do that, first we have to talk about slopes. In a 2-dimensional graph, slope is pretty simple. Like, the slope of this line is just the rise over the run. Pretty simple stuff. When you're doing calculus, you're able to use like derivatives to find tiny, tiny slopes that allow you to make tangent lines. And it's just as simple as that. From there, all you have to do is take the slope you got from the derivative and plug in your y equals mx plus b. Simple. That's just how you found the tangent line in Calculus 1. The issue here is that slopes in 2-dimensional graphs are just... let me make that a little bit smaller. Rise over run. Delta y over delta x. We have no, like, way to describe this, or we obviously do because we're doing it, but we have no fractional way to describe this in 3 dimensions. There's no, like, delta y, delta x, delta z. At least not like that. It can't be described with fractions. The way we describe it is with vectors, because vectors can point in directions in 3-dimensional space, and like 4-dimensional space if you wanted to go there, wherever you want. Just the number of things you have in a vector denotes the amount of dimensions you want it to go in. So that includes 3 dimensions. We can have a vector in 3 dimensions, as everyone in multi should know. But the nice thing about vectors is that they allow us to describe a slope, per se, in 3-dimensional space. If you have a line, a straight line, let me draw a thingy there. If you have a straight line, say like that, I don't know if that looks 3-dimensional, but actually, let's make it off the origin, like that. That does not look okay, like that. Yeah, that works, I think. You can represent the slope of this line with a vector that stems from the origin and is parallel to this line. And this is helpful because it allows us to describe slope in a specific way in 3 dimensions that is, like, understandable. So how would we find the... I'm gonna refer to this as the slope vector of a line. So this slope vector is like the slope of this line. Let's say our line was parametric equation of x equals 3t, y equals 2t, and z equals t. Then the slope vector would be 3, 2, 1. Because essentially all it's saying is that for 1t, you're going 3 in the x direction, 2 in the y direction, and 1 in the z direction. So you can describe that with a vector that goes 3 in the x direction, 2 in the y direction, and 1 in the z direction, which will meet, like, I can't really draw that, but you get the picture, right? So it'll go like that. Yeah, I think that's a pretty good example. And that